Hello. Sir, good morning, sir. Narendra, sir, good morning, sir.
Good morning, ma'am.
Sir, this is Madhuri. Sir, can we test the screen, sir? Once, let us test the screen, sir, whether it is visible or not. And we'll start the
Yeah,
session
yeah.
at 10 o'clock, sir.
Please allow my video.
Sir, you are co-host, sir.
Okay,
You have all permissions, sir.
okay.
You are visible, sir, now on the screen.
Yeah. Can you see my screen?
Yes, sir. Screen is visible, sir.
Okay. Okay, fine. Everything is good. Okay.
Okay, sir.
Please tell me when to start, है ना?
Okay, sir. I will start sharply at 10 o'clock, sir.
Okay, okay. Sure.
Thank you, sir.
ఇస్రో సైంటిస్ట్ చాలా బాగా చెప్పారు. చూసారా? అసలు భలే చెప్పారు.
Hello.
Yes, sir.
Sir, am I audible?
Yes, sir. You're audible, sir.
Yes. Good morning, Narendra sir.
Sir, good morning, sir.
Good morning, Dr. Ravi.
Sir, how are you, sir?
I'm fine, sir. How are you?
Sir, fine, sir.
Right.
I think today is holiday for you, na, sir?
Not basically. NIT Raipur is open. Means NITs and IITs, they do not have the holidays today.
Okay. Basically, all the private colleges, they have given holidays, I think so, throughout India.
Okay.
Today is a good opportunity for the participants. They can learn from their home. Today is just a mock
Right.
free, na, sir? If it is open. I think today's session is very useful to the participant because I saw your resume and I heard from your friends regarding your biodata and your research work. I think it's very useful to the participants.
Thank you,
Good.
Dr. Ravi. I will give my best, and I will ensure that so your participants learn something fruitful from my presentations today.
Thank you,
Okay.
sir.
Sure.
I'm requesting all the participants, please learn something, and also these learning information should be reflect on the student. This is a main motto for conducting such type of these AICTE sponsored FDP like that. So anyhow, all the best to the participants, and thank you so much, sir. Even though you're having some administrative works and some additional works in your organization, even though you're accepted our request, and once again, thank you from my department and from our institution. You are showing on the concern on our department and our institution. And thank you, sir.
Thank you, Dr. Ravi, for inviting me. I thank the administration of your institute for arranging such a useful faculty development program. Okay, the theme and the resource persons that you people have selected, they are really they are the renowned people, and I really hope that all the participants are going to benefit a lot from this program. The content means the theme of your program is really as per the need of the present time. So I really hope that all the participants will get benefited, and they will learn. They will be able to initiate the research in this field as well, with whatever the learning they will get from this program. So thank you once again, Dr. Ravi, for inviting me.
Thank you, sir. Thank you, sir. Thank you so much, sir. You are so much related. Thank you, sir. Madam, go ahead, please.
Okay, sir. Thank you, sir. So, a warm welcome to all the participants for day 11, session 1 of AICTE sponsored 2-week faculty development program on machine learning in image processing applications. I would take privilege to introduce today's speaker, Dr. Narendra sir. Dr. Narendra D. Londe sir is an associate professor at NIT Raipur. Sir has completed his PhD from IIT Roorkee. His area of research interests are medical signal and image processing, machine learning, pattern recognition, medical ultrasound, biometrics, brain-computer interface, speech signal processing, deep learning, biomedical instrumentation. Sir has published 50 international SCI index journals and 28 international Scopus index journals, and he has published more than 40 international conferences publications. Sir is a principal investigator for 5 sponsored projects worth more than 20 lakhs. And present, he is working on machine-based behavioral multi-parametric pain assessment system, which worth 23 lakhs 56,000. Sir has guided 12 PhD students and 17 MTech students. In his credit, he has received many awards. He received Best Paper Award for published research article in Journal of Medical Ultrasound, which is an Elsevier publication, and this award included a visiting scholarship to attend 30th annual convention of Taiwan Society of Medical Ultrasound. He has also received T.K. Saxena Memorial Award of Ultrasonic Society of India for best PhD thesis in the field of ultrasonics. He has received Best Paper Presenter Award for the paper presentation in IEEE conference and received NIT Raipur Best Faculty Award 2019 on Foundation Day celebration of National Institute of Technology, Raipur. Sir has many memberships. He is a senior member of IEEE. He is a member of IET, and he is also a member of Institution of Engineers. He is a member of Ultrasonic Society of India. He is a member of Acoustical Society of India. He is a life member of Biomedical Engineering Society of India and life member of Telemedicine Society of India. He is also a life member of Instrument Society of India and life member of Institution of Engineers. Sir, we are very delighted to have you on today's session, sir. Thank you so much. Sir, please take over the session.
Thank you, ma'am. Thank you for the nice introduction. Now, I would like to start my presentation. See, participants, the theme of the program is machine learning application in the image processing. Okay, so basically, what we need to understand that there are different different images. So when we say digital images, it's not like only photographic images are there. There are medical images as well, isn't it? So a machine learning engineer, a data scientist, or even any engineer, if he or she is contributing towards understanding that images, okay, getting a useful information from that images, so that whatever the whoever is going to benefit from that images will get the benefit in a wider spectrum. Means the things which is not which we are not able to see with our bare eyes or with the naked eyes, that things need to be extracted by doing the image processing, basically. Okay, that is what is the expected from the technical fraternity. Okay, so here in my presentation, basically I am presenting you that how we are going to do a useful task useful task on the medical images, so that the radiologist, the person who actually assess the images and prepare the report of the medical images, and giving a understanding to the doctor who is treating that patient, that what kind of disease that has been found in the images, what is the growth of that disease, whether it is severe or not, what further investigations are required. All that is reported in that by the radiologist in that report. But basically what happens in doing all that things, he has to take a lot of work. Okay, he has to put up a lot of energy. He has to very attentive. He need to be very precise, very accurate in finding out that particular doing that diagnosis, okay, from the medical images, which is very what I will say is having a very good chance of finding errors. Okay, because whenever say that, let me just give an example, that there is some, say, intravascular ultrasound imaging is being conducted by the radiologist. He has to assess more than 2000 slices, more than 2000 to 2500 images. Now just imagine how he will be able to do that, checking each and every image and finding the abnormality in that image, and doing all the measurements on that images, and reporting that in his report. Okay, so this is a very tedious task, and it is really possible that they can do some errors. So exactly in that case, it is really a good idea. It is a really good thing that if we provide some automated systems to that radiologist, some computer-based systems to that radiologist, so that all the data, all that image data can be automatically analyzed. Okay, automatically particular that abnormalities, detection of that particular abnormality, then assessment of that abnormality, whether how much is the severity of that abnormality is there. If that is being done automatically, then it is going to save a lot of time of the radiologist. In fact, why it is required, let me tell you that also all over the globe, if you just go to the reports of the World Health Organizations, you will come to know that the patient-doctor ratio is very high all over the world. Okay, in fact, if I will tell you that it is somewhere 2000:1 in some countries. Okay, 2000 is to 1. It means that for 2000 patients, there is one doctor is involved. So you just imagine how valuable time they are having. Okay, how valuable their time is, and whatever the technology assistance that can be provided to them, so that that valuable time can be saved in doing all this assessment on the data, medical data, that is going to be a very good research for the engineering fraternity or technical fraternity. So with that view, many researchers are working on building or developing the automated computer-aided diagnosis systems, which can automatically detect the disease, detect the abnormality in the medical images, and assess that, finding the severity of that abnormality, and give a report only based on the images, that too in a very accurate way, whether that particular abnormality is cancerous or not. Okay, because many times what happens that radiologists find it that yes, there is a suspicious, okay, and thereafter again some pathological tests need to be followed to find out whether it is cancerous or not. But yes, there are many computer-aided diagnosis systems that has been proposed by the researchers, which can only detect the malignancy of any abnormality in the images, okay, abnormal part in the images, medical images, by using the computer-aided diagnosis or computer-aided methods. So this system is not only saving their time, but it is also saving to go for further further pathological test of that for the diagnosis of that patient. Okay, so that is what is the motive of my research as well. And just like many researchers in this field, I'm also doing work in this field for last now almost 14 years. Okay, and I had work on different medical image databases, right from ultrasound, computed tomography images, MRI images. Okay, even we are working on the photographic images, which are being taken for the psoriasis patients. Okay, so this is how even we are working on the EEG signals, ECG signals. So we are working on in the signals as well. Okay, so with this introduction, I would like to start my presentation. Okay, the topic of my presentation today is medical image segmentation and classification using deep learning. Okay, now the first thing that comes in our mind, that what is this medical image segmentation and classification, and why it is required, right? So let me just tell you that healthcare industry is the most priority sector, because if you will see the today's time also, the pandemic situation that today is, everybody is dependent on the medical fraternity, or it is depending on we are in the need of a very good healthcare, right? And in this, medical imaging plays an important role in the disease diagnosis, right? Even if you are nowadays, what people are doing, that COVID patients are going for the chest x-rays, and the infection of the chest is actually confirming whether some person is suffering from the COVID or not. And many research papers or many research studies are being published on that. Okay, so what is the reason? Because the medical imaging modalities today, the present status of the medical imaging modalities today is really good. They are of very good quality. They are having a significant information. And if we do a processing over that images, we can surely avoid further pathological testing or involvement of the human medical experts in only just doing the assessment of that images, right? So these medical imaging modalities are non-invasive. They are also invasive. Imaging is also involved there. There are different processing in the say that the radiologist see the some tumor is there, then he do the measurement of the tumor, putting a line to measure the length of that tumor, width of the tumor, circumference of that tumor, doing all that things manually. They need to do it manually on the computers, right? And there are many softwares which are being provided by the companies, those who actually prepare those medical imaging devices. they need to work on those softwares. In that, whatever the interpretations of the medical data is there by the domain expert, okay, so that interpretation basically based on the selection preferences of the medical expert, that whatever the medical expert is who is actually assessing that medical data, medical images, his selection preferences, that say that what in that image, or he has to decide that what part of the body needs to be imaged. He has to decide that if there are 2000 slices, he may skip, he will take first slice, then maybe 10 slices, he may be skipping some slices because there is a lack of time to them. Okay, and that is why there, whatever this manual interpretation of those medical expert is there, it is totally subjective and it is complex as well, right? Because it involves extensive variations. Extensive variations are involved there, and the reasons for that variations may be the artifacts. There may be some noise in the images because of different sources of the errors, right? There can be a problem of inter and intra observer variability. What is inter and intra observer variability? Basically, that two medical experts can have a different opinion on the same images, okay, on the same patient, okay. At the same time, it may also happen that the same medical expert can have two different opinions on the two different visits of that patient, okay. On the different two occasions for that patient can have a different opinion. So that sort of problems can happen in doing this manual interpretation by the medical experts. And second thing is that, as I told you, there are many there is involvement of the investigation of many images, okay, thousands of images is required there. So it is totally totally understandable that the task is tedious and they may suffer from fatigue, okay. They may get bored, or they may get diverted, or they may not remain attentive. They may get exhausted by doing that work, right? So that is why it is really important that we develop an automated computer-aided diagnosis system for medical imaging evaluations, so that the diagnosis performance can be improved and we can reduce the manual errors. So that is only the main motive of the whatever the work that is being carried out by many researchers in this field, right? So with this motive now, there are many researchers going in the field of X-ray imaging, then ultrasound imaging, CT imaging, PET imaging, positron emission tomography, then magnetic resonance imaging. And whatever this research is going on, this research is, there is a huge research involved into this. The reason for that, because the medical imaging modalities are different. Many medical imaging modalities are there. At the same time, there is a variety of the organs also. That yes, human have many organs in their body. So lung, then there is kidney inspection, then there is a heart, then there is, so medical expert or the radiologist who is taking the image, he will not be said to to capture the images of only the cardiac imaging he will be doing. It's not like that. He need to take the images for the different organs. So there is a variety of data that he needs to handle. At the same time, there is a variety of diseases as well. Okay, somebody may have lung cancer, somebody may have lung infection, pneumonia, and all that things. And for that, the researchers or the expertise is required. Okay. So when we design any cardiac system, basically, what do you understand by the cardiac system? Cardiac system in the sense computer-aided diagnosis system. So when I say computer-aided diagnosis system, first of all, what you need to do, that you have to detect the abnormality in the image. Okay. So in technical terminologies, we call that thing as a image segmentation. Okay. So I will find the abnormality in the image and I will trace that abnormality. Okay. So that is what is called as image segmentation. And thereafter, when I find that abnormality, I will
remove that patch from the image and give it to my classification process, where by extracting the different features from that patch of images, patches from the medical images, my classifier will learn that when there are features like this one with with the patches of those medical images, then this particular patch is malignant or cancerous. Or it will also learn that if the patch is like this one, if these are the features of that patch, then it is not a cancerous. Okay, so basically, just by looking barely with the naked eyes, looking at this image, the medical experts may not be sure about whether it is cancerous or not, and they would like to go for some pathological test like physio, that biopsy and everything, and thereafter they confirm whether it is cancerous or not. But computers, from that image, they can extract many features. Okay, like say gray level concurrence matrix is there, then there are GLCC features are there. So by observing those features, if you extract those features are numerical values which are being actually calculated with the mathematical formulas from the images, and those values will be able to easily discriminate between two images that yes, this is cancerous and this is non-cancerous. So if you have some large number of images where the ground truth is available, yes, that this is a one image, this is one abnormality, this abnormality has been tested with the biopsy, and we come to know that when the abnormality is having this abnormality is there, then that abnormality is cancerous. So if you have that ground truth, and if you train your computer network, okay, computer algorithm with that data, with the images and with the ground truth, then your computer algorithm will learn. That is what is called as machine learning, isn't it? So with this, in the computer-aided diagnosis system that we are able to understand, there are basically two important tasks involved. First one is the detection of that particular abnormality, right? So when I say detection of that abnormality, it means medical image segmentation. That is image segmentation. Okay, so you can see here in this image that we have segmented one lymph node in a CT image. Okay, that is an abdominal CT image is this, and this is the lymph node that we had detected automatically in that CT image. Okay, so see, when we are developing any computer algorithm for doing image segmentation, it becomes very challenging when your background is also the object and the backgrounds are having the similar structures or similar gray levels. So in that case, it is really difficult. But yes, nowadays with the advanced machine learning algorithm, it is really possible to do the segmentation of those abnormalities in the images like this one, right? So you can see here we had segmented this lymph node here, and we had generated its mask. You can see here exactly that that area has been traced and it has been removed from the image. So that is its mask that is I am showing here in on the screen. This is another example of image segmentation. Here you can see this is a lung CT image. That is an actual lung CT image. And in this image, what we have done, we have first removed the lung parenchyma like this one. You can see this lung parenchyma has been removed from that image, from that CT image. And in that lung parenchyma, we have done further segmentation of lung nodules. You can see these red circles are there. Okay, this is also visible in more clearly in this my image. Now you can see these are the nodules that has been segmented. Okay, so segmentation or detection is the very important task, and which is and equally challenging, because the images, medical images, are having very similar gray levels for the different biological tissues. So it is really important that your computer algorithm should detect the correct biological tissues instead of giving the wrong segmentation. So if it is being done by the computer methods, then it is really a major contribution to the field of medical imaging, right? Here again, as I was showing you that first lymph node image I was showing you, the similar here again, abdominal lymph node image and mediastinal lymph nodes are detected automatically by using the computer algorithms here. And this is just an example to show you that yes, this is how the medical image segmentations are need to be done, that abnormalities need to be detected in the medical images. Okay, this is another example of intravascular ultrasound. As I told you, here in the intravascular ultrasound, what happens that there is a catheter. That catheter is having one ultrasound transducer at the tip of that catheter, and it is inserted into the artery. Okay, and wherever that artery is having the calcium, if the calcium deposition is there in the artery, then while removing that catheter from that artery, it starts to capture the ultrasound images. And in that ultrasound images, this is where you will be having your catheter, and this is the inner boundary of the artery, and this is the outer boundary of the artery. So inner boundary and the outer boundary we have segmented here. We have removed the catheter region, and in that inner boundary and outer boundary, you can see this is the white region is there. So this white region is indicating that it is having the calcium in that artery. And you people are very much aware that if this calcium deposition is increased and it becomes severe, then what will happen? It will block the artery, and due to that, a person may suffer from the stroke or maybe the heart attack. If it is a cardiac artery, then it will be suffering from the cardiac heart attack. Or if it is the artery going to the brain, and if it is getting blocked, then somebody is getting a stroke as well. Okay, so it is really important to understand that how much calcium is deposited in that artery, so that unnecessary medical procedures can be conducted. Say that the calcium is it is not severe, but yes, it is there. Then doctors advises that you put up the stent and enlarge that artery. Okay, or if the calcium is very high and we know that it is going to stop the blood flow at any moment of time, then they suggest to do the bypass surgery, putting another tube parallel to that artery, so that the blood can flow through that tube instead of flowing through that blocked artery. Okay, so that is why such investigations are very important. So here in this work also, this work, what we had done, we have segmented all the calcium deposited in the artery, and we have done it in all the slices. As I told you, intravascular ultrasound slices are having 2000 to 2500 images. So we have done that for all the slices, so that it's not only finding out the area of the calcium here, but if we add up all that area for all the slices, I can also find out the volume of that calcium, that till what up to what length of the artery that calcium is available, and what is the volume of that artery, volume of that calcium present in that artery. If it is, that is how we are going to understand the severity of the calcium deposition, and we can understand, doctors can understand that yes, the patient may suffer from any problem. Okay, so this is what exactly is the segmentation is all about. Now, when I talk about classification, as I told you that once we have the segmented regions, now I want to know whether that segmented region or that segmented abnormality, whether it is dangerous or whether it is cancerous, malignant or not. Okay, so doctors, by just visualizing that patches, they cannot assess it. They will further ask for the pathological test, do some biopsy of that particular those abnormal tissues, and from that you find out whether it is cancerous or not. But yes, in today's era of machine learning and the deep learning, we can even do the even find out, we can develop a network which can be trained with the images and the biopsy reports, where it is confirming that yes, this image is having cancer. this image is not having the cancer. Okay, this image is having the cancer. This image is not having the cancer. So with that data, our current machine learning and deep learning algorithm learns from that data, and they learn in such a way that they do not actually those algorithms are not giving the image, they are actually extracting the information from that image, and based on that information they are confirming, yes, this information means cancer, this information means non-cancerous. Okay, so that sort of intelligence is not there with the radiologist, and that is why this artificial intelligence is being used to do the assessment or finding the severity of the abnormality. Okay, so if I'm doing that task, that getting my segmented images, and then I'm feeding it to a classifier where it is able to tell me whether that image is having the cancer or not, if that sort of task I'm performing, I call that as a classification task. In technical terms, we call it as a classification task. So that is what is the medical image classification. So basically, for any medical image diagnosis system, there are two major stages. First one is the medical image segmentation, and second is the medical image classification. Okay, so here you can see these are some of the sample lymph node images, or I will say image patches, that these are the segmented lymph nodes that we had extracted from the CT images, and we've come to know that they are, this row A are having the patches of malignant lymph nodes, and this row B are having the patches of benign lymph nodes. Okay. Now, what are the challenges in doing the manual medical image segmentation and classification? Means whatever the radiologists do that manually, there are I have already told you about all these things. They will be requiring great expert anatomical knowledge of all the body parts, and what are the blood arteries, where they are flowing. Everything is really important, will be required. That manual assessment can suffer from the inter and intra-observer variability. That is already I told you. It is expensive as well. Why expensive? Because we have to put up the many human resources. We have to put up the human resource for doing all that task, which cost us a lot. Instead of that, I can develop a system and I can put up one computer, and he will do that task for if that computer does the task automatically, then all that human resource costing can be avoided, or it can be saved. Okay, it is a time consuming for the human beings, medical experts. It is very time consuming. It can be very exhaustive to them. It can develop a fatigue for them. The performance gets affected in different acquisition protocols and different artifacts. So if the performance of that manually doing the segmentation and classification, radiologists do the segmentation. They manually trace the abnormal part of the images, and then they do the measurement. The length is this much, the width is this much, and after that they give some initial assessment, and they may prescribe for the higher further pathological test. Okay. And at the same time, there can be a large within class appearance, location, and pose variations as well, because when the images are being acquired, there is a possibility that at one visit, the patient is having some images, and on the another visits, if it is missed by imaging the exact similar part, or there can be even pose variations are possible. There is a problem where when the abnormality is locating at different places in the body. Okay, so that sort of problems create a lot of issues to the radiologist, right? If we do the computer-aided diagnosis system or automated diagnosis system, if we develop, then we can save. We can do very proper and detailed diagnosis. It will be provide diagnosis in a less time. It will be cheap as well. It will not be requiring too much anatomical expert knowledge, because it will not be actually depending on the that knowledge. It will be depending on the training, and that training will be from the image data, image features. not from the anatomical or expert knowledge, right? So it will also can help to decide on the theory and planning that if your computer diagnosis system is assessing one patient on 2 different visits, so it can tell you that yes, the cancerous tissues in this particular patients are increasing, okay, or it is becoming severe. So doctor, according to that, doctor can plan a therapy, okay, or it can also decide the therapy, that which therapy that doctor should use. And it helps in computer aided surgery also, and that if you are doing the surgery, then that this information can be helpful. It can also helpful to decide finding the therapy responses, that whatever the treatment being given to that particular patient, whether that treatment is working or not. That can also be, because if some patient is having some abnormality, and if he or she has been given some treatment, some medication, so in the next visit, you can assess that if that particular abnormality is reduced, so you can say that yes, the treatment is going well, isn't it? So that way we can also evaluate the therapy responses. It can also help in designing the drugs as well, that whatever the medication that need to be given to the patient, that can be decided based on this, because as I told you, in intravascular ultrasound, how much is the volume, how much is the area, okay, how much is the length of the arteries having the calcium, all that will decide that what medicine need to be given to that patient, okay. So that is why these are the important these are the benefits, and they are very important parts of the cardiac system, that is medical image segmentation and classification, right? Now machine learning has evolved now in last 2 decades, and conventional machine learning is actually replaced, or it is being overcome by its advanced version, that is called as deep learning. Now why it is getting so popular, why it is being used so widely, the reason is that it extracts the multiple levels of the features. Means, say that if I am doing machine learning, I have to do first feature engineering. I have to extract the features from that my data input data, and it is up to me. It is I have to decide that what features I will extract. So I will have the limitation. I will study the literature, and as per the literature input, I will extract some features. But those features may not be good enough, or may not be sufficient to do the task of diagnosis, isn't it? So it is somewhat limited to or dependent on the human expertise. Okay, it will be somewhat dependent on the data scientist, or the person who is machine learning engineer is there. So it will be depending on that particular person's experience, its knowledge, his expertise. It will be depending on that. Okay, so but in deep learning, what happens that you have to give only the raw input images, okay, and you have to design your deep learning architecture in such a way that it will be extracting the features on its own, and that will be multiple level of features, means abstraction, representation, then information. Okay, when I say abstraction, in the sense, that is a say that I am having one tumor is there. So if the edges of the tumors are being found out, that is an abstraction. Then representation, that yes, this tumor is having this size and that size and all that things. Then that from that for the tumor, if I further find out some features, those who are giving the specific information about the tumor, then I will call it as a tumor information. So it means that it is a multi-level features extraction built in itself. Deep learning is having that in itself, that it will do the high-level feature extraction as well, medium-level feature extraction as well, low-level feature extraction as well. Okay, so that is how it will be learning on its own from the input data, and that learning or that will be based on quality and complete features, as well as what I will say, very precise feature discriminant values can be learned by your network. Okay, if I do the conventional machine learning, I only need not to do the feature extraction. I have to further do manually the feature selection as well. Means if I extracted 100 features, maybe those 100 features are not useful and they do not carry the useful information. Then in order to learn my machine learning algorithm from that features may reduce the performance of my machine learning algorithm. So I have to specifically select some useful features from that extracted features, and I have to give that selected features to the machine learning. Then my machine learning algorithm will be able to do the intended task. So that is what is there. So it means that it is conventional machine learning algorithms are majorly dependent on the handcrafted features, which is not there at all in the deep learning. Okay, so that is what is the advantage. And deep learning techniques are capable to handle extensive variation from patient to patient data. The reason is that as it learns from a larger data set, so when you are giving the larger data set, you can give the variation in the disease also, you can give the variation of the patients also, that yes, I'm giving it for male, females, from this age category, from that age category, and I'm giving it for the, say, only for the lung cancer. So I'll be
For inconvenience.
Please
Please
start my
be
video.
online.
Yeah. Yes, I'm back.
Okay, sir. Thank you, sir.
Okay. So what I was telling here, that there is a lot of manual work is involved here for the data scientist as well. So doing that manual feature selection, extraction, that will take a lot of efforts, right? While in case of deep learning, you just have to give this input images and to this deep learning architecture, and it will be doing all this tasks on its own. Okay, it will be doing the extraction of the features as well. It will learn from those features and it will do the intended task of diagnosis. Okay, we need not to worry about it. But the thing is that we have to be very careful in designing that deep learning architecture. We have to ensure that with respect to your data, imaging data, there are levels in the different levels in the deep learning architecture which can extract high level, medium level, low level features. All the features from that, we have to also put up many other what I will say, new trends in the deep learning, like attention mechanism. Then there is a dropout layers is there. Then there is a residual mechanism is there. So we have to only work on designing the deep learning architecture. Okay. Rest, once we are done with the architecture designing, the rest will be done by that deep learning algorithm. Okay. And that is a one-time effort that we have to put in designing that deep learning architecture. Thereafter, that deep learning architecture will doing the intended task very precisely, right? So this is when the deep learning has started, it is started from the very first network, that is a convolutional neural network. Because why this is we need to understand, because most of the parts in this convolutional neural network are the basic elements that are being used by different further deep learning architectures. So that is that with that intention to understand the deep learning methods, I'm describing here this convolutional neural network. So this is the first deep learning architecture which was proposed, and it was actually designed for the images only. Because what was happening in the, if I go 10 to 20 years back, there was neural networks as well, but those neural networks were not able to work on the images. So when people had got an opportunity to advance it, they had started it for the images first, right? And it is not like that when neural network was designed, that time they were not aware that if I am increasing the hidden layers, so the learning of my neural network is going to be far better, it is going to be deeper. They were aware, that was already aware about, that was already known at that time itself to the scientist. But what has happened, because of the computational limitation of your computer machines, okay, and the non-linearity in the data was there, and there were not good activation functions was there, or membership activation functions were there which can handle those non-linearity. So that is why it was not that popular in that time, but now it is very popular, that deep learning methodologies. The reason is that today the computational complexity has been increased of your computer systems. Second, your storage is very huge now, terabytes of data, gigabytes of data can be processed by your computers. Okay, you have clusters, supercomputers now. They can process large data, and this is the only requirement for the deep learning architecture, is that it requires a lot of data so that it can learn in a deeper sense. It can learn more from the data, and once that learning is, if you will increase the learning of your net architecture, its performance will increase. So if you see the deep learning architecture's performance, you will see that as you increase the data size, the performance of your deep learning architecture increases, right? So now that computational algorithms, computational efficiency is there, computational power is there today, there is a huge storage is there. And third thing is that, yes, we have the activation functions which can handle the non-linearity in the data. Okay. So we have the solution to the non-linearity of the data today, and that is why this has become a reality today, that we are having the deep learning architectures which have involved many hidden layers in that architectures, and they are able to learn a lot from the images. Earlier that thing was not there. Even if you will see the conventional neural network at that time, it was even not being applied for the images. The reason is that image we used to give images in a single row matrix, okay, a column matrix. So every pixel value is going to be, say that my image is of 256 by 256, okay, and if I'm giving it as a column matrix, I have to have 256 into 256 neurons in the input layer, and thereafter it is going to be given further to the hidden layers. So that was the problem that time. Okay, and handling that much huge data was not possible, but now it is possible. Okay, so now let's look into this convolutional neural network. This is basically having the hierarchical feature extraction is there. As I told you that all the deep learning architectures as having the hierarchical feature extraction, it initially extracts the low level features, then medium level features, and then high level features, and that is how they learn from the input data. Now in this, the very important task is the convolution. Here you can see these are the filters here. These are the filters here. These filters are being actually convoluting with this images, and that is why it is called as convolution algorithm, convolutional neural network, right? And once the convolution happens, then that output of this convolution will be given to the activation function, where it will be, that is the heart of the neuron, isn't it? Any neuron will decide the output of the neuron will be depending on the activation layer. So this convoluted data will go through this activation layer and it will decide, yes, this is the response of the neuron. Okay. Then there is a pooling also, that whatever the response of the neuron is there, that response will be having many data points or numerical values, or it will be a huge matrix. Okay. And in that huge matrix, there can be the local information can be represented by a single value. Okay. So that is why there is a pooling is being applied there. Instead of taking all the values, the local representation is given by a single value. Say that I'm doing max pooling. So what will happen in a matrix of say 2 by 2? I'll be selecting the maximum value, and that will go ahead in the next layer. Secondly, there is a dropout layer also. I will give a brief here. You can see this is how the convolution will happen. You can see this is your convolutional filter, and this is your input image data matrix. And this convolutional matrix is actually getting convoluted with this image. And you can see when the convolution is happening, this is the convoluted features that will be generated. So when I'm doing the convolution, it means that I'm extracting the features. And when I'm giving that features to the activation function, it means that my neuron is working. Okay. So that is how this works. Second, as I told you, that activation layer is there. So that activation layer will have some activation function. So very popular activation function with the deep learning architecture is the ReLU, rectifier linear unit. Okay. Why it is being used? Because it is faster, it is less expensive, it is more expressive, and it is having the gradient vanishing problem. Gradient vanishing problem, it means that, as I told you, that if you are doing the tuning, the performance means the extraction of the features from the low level, medium level, and the high level, means the gradient is increasing. It is not going up and coming down and then going up and then coming down. That should not happen. So that is avoided by this ReLU. And this ReLU, if you will see this activation function here, it will allow only the non-zero values. Okay. Non-zero values will allowed, and rest all the values 0 and less than that will not be allowed. Okay. So this is how it works. And this is the max pooling layer. So you can see here, when I'm doing this matrix here, say that I'm doing this matrix. So instead of taking all these 4 values, it will be taking the maximum value from this matrix, that is 6 here. So this 4 by 4 matrix that is having the 16 elements, 16 numerical values, is now reduced to a 2 by 2 matrix, which will be having only 4 numerical values. So that is how we can reduce the data. See, that is also very important, that handling huge data will not be easy. So better you find out the representation of the local information. If you can do that, if you can reduce the data, that is a good thing. And that is what is possible here by doing the pooling. Then there is a dropout layer also in some of the networks that we apply. What is this dropout means? Dropout means whatever the neurons are there in this, say that this is my neural network. So I know that some of these neurons are here, which are not contributing to the performance of the intended task. Okay. So those neurons will be omitted. They will be avoided. And that is what is called as dropout. Okay. But you have to understand that whenever you put up the dropout layer, if after putting the dropout layer, that in that dropout layer, it will be randomly dropping the neurons. And with that dropping of the neurons, if your performance is increasing, then you can say that yes, your dropout layer is contributing. If it is not contributing, you need not to put it into the network. You can remove it out. So this is all about medical image. This is all about the basics of medical image segmentation, classification. I also told you, because with my title, I am giving you the brief introduction first. So I am done with my introduction. As per the title, medical image segmentation classification using deep learning, I have introduced you what is medical image segmentation, what is medical image classification, and what is deep learning, isn't it? Now, let me give you one of our study that we had conducted by my team, and that work is nothing but the lymph nodes detection and classification in computed tomographic images. That is what we have done. Okay, so let me tell you about the lymphatic system first, that why we have done this work, why we have detected the lymph nodes, and why we have did the classification. There must be a reason for that. So for that, we need to understand what exactly these lymph nodes, where they are present, what is their role, isn't it? So let me just brief you that information. There is a lymphatic system in your human body. What is this lymphatic system? It plays a vital supporting role for cardiovascular and immune system. Okay, whatever the blood which comes from the heart, that blood carries both the immunity power, or what I will say plasma, that proteins and vitamins, all that immunity is there in that blood at the same time. Okay, so whenever the blood comes from the heart and goes to the tissues, so this is a total process. Then it get deoxygenated. Okay, after interacting with the biological tissues, when that blood is supplied to some organ, and after doing the supply of the organ, the blood will become impure, and then it will go back again to the heart for the purification, isn't it? So if you will see that process, it is basically 20 liters of blood per day through the capillary filtration goes to the human organs. Total circulation system is there. It actually performs the circulation of 20 liters of blood in one day. Okay, in that circulation, it actually removes the plasma and leaving the blood cells. This happens when they are interacting with the biological tissues. Okay, so when some blood reaches to the biological tissues, so biological tissues will use that blood. Okay, and after using that blood, it will separate that into two parts. First one is the plasma, and second one is the blood cell. So roughly 17 liters of the filtered plasma are reabsorbed directly into the blood vessels. Okay, while the remaining 3 liters remain in the intestinal fluid. Okay, now whatever that plasma is there, 20 liter blood is there, so 17 liters of filtered plasma, which is having the blood cells and the many other proteins and your immunity components are there, that will be carried by that plasma. Okay, one of the main function of the limbs, that is what is the work of the limb system. Okay, to avoid the accessory return route to this blood for the surplus 3 liters. Okay, lymph is a fluid that actually circulates throughout the lymphatic system. The lymph is formed when the intestinal fluid is collected through the lymph capillaries. So let me just show you with this diagram. You can see here, this is the blood which is going to the different biological tissues in the body. Okay, and after this, this is the blood which is returning through the veins, and this is the lymph that will be flowing through the lymphatic system, right? Now, when this lymph flow through the lymphatic system, these lymphatic systems are having the lymph nodes here. You can see these are the lymph nodes. So these lymph nodes are like filters, and they remove the viruses and the bacteria present in that lymph. Because that is a vestige, and from in that vestige it may have some bacteria. Because when this pure blood is interacting with the biological tissues, so those biological tissues may be infected with the virus or bacteria. So that will be taken by the lymph, and that is going to be filtered here by the lymph nodes. That is the work of the lymph nodes. So whenever some cancer happens to any patient, say that I'm having a lung cancer, so lymph nodes related or close to the lungs will be having the first symptoms of the cancer on those lymph nodes. So if you people are assessing the lymph nodes, then you will be able to learn that yes, this particular patient is having the cancer in the lung. Okay, so that cancer can be detected by understanding the lymph nodes. So if you see the lymph nodes present in the human body in the lymphatic system, there are total 450 to 500 lymph nodes in the body. And if you see, they are present like this one. You can see there is this is cervical region, then there is a supraclavicular region, axillary region, mediastinal region. Okay. Then this is a abdominal region, and it is having many lymph nodes there. Okay. Even at the elbows, at your knees, you are having the lymph nodes. Okay. Now, whenever the cancer happens, these cancer cells not only affect the particular organ of the human body, but it also spreads to other body parts. And this process is called as metastasis. Okay. Lymph nodes are often the first organs in which the metastasis forms. So whenever that cancer spreads, so the first, because as the very next system to any biological tissue is the lymph nodes. Okay. So that is why that particular cancer can easily go to the lymph nodes. Okay. And that's why this lymph nodes necessarily considered, that's why they are necessarily considered to be examined for all kinds of cancer. So if you are having a cancer or not, so doctors or cancer specialists will be seeing it first on the lymph nodes. Okay, because they are widely distributed throughout the body. This cancer causes affected lymph nodes to be enlarged. So whenever the cancer happens to the lymph nodes, so they becomes larger in size, and and in order to assess the progress of the disease and to check whether the treatment is effective or not, physicians are basically see the statistics of the lymph node, or they actually monitor the lymph node enlargement or its enlargement or its contraction to understand the cancer, its treatment and everything, right? So lymph node metastasis also gives information regarding nodal stages from the proper selection of the therapy, that if somebody is being given some treatment regarding the cancer, the effect will be assessed at the lymph nodes first, right? So that is why this lymph node detection in any medical images is very important. Okay, with that view, we have taken up this task that yes, lymph nodes are so important in detecting the cancer and in treatment of the cancer, and in also understanding the effect of the therapy of the cancer. Okay, so that is why we have taken up this task to do or to design automated computer-aided diagnosis system for the lymph nodes. Okay, so this manual segmentation of the lymph nodes, if I'm doing in as you can see, the lymph nodes are 450 to 500 in numbers, and they are present in different parts of the bodies. Okay, so you have to take the image, and in that also, if you see the size of the lymph nodes, it will be less than 10 mm also, 10 mm. So you can see how small structure it is. It is how small size those lymph nodes are having. So with such a smaller size, detecting such a smaller size elements in the images is really difficult. Okay, and that is why there is a sure possibility of inter and inter-observer variability, because they are smaller in size. Their structure is very similar to other body organs or other biological tissues. They're circular. Okay, there can be something else which can also be circular. So, and the gray levels are very similar. So it is really difficult for understanding the abnormality in the lymph nodes manually just by looking at the medical images, right? It is having the low contrast. It can have the noises, and that is why many enlarged lymph nodes lie directly adjacent to each other also, and that is how they form the clusters, and that is then it becomes really difficult. Okay, there is a problem of the class imbalance also. Class imbalance in the sense that if you're taking the abdominal image, so it will be having the lymph node as well as it will be having other biological tissues as well. So if you will consider that yes, there are 5 only lymph nodes are there, and there are 20 other biological tissues present in that image, then detecting it by using any computer method, a computer algorithm, so that computer algorithm has to will suffer from the problem of class imbalance. Okay, means for that particular class of lymph node, the number of biological tissues are less compared to the other biological tissues. So there will be a class imbalance problem when we will be doing that thing automatically, right? So you just see here, this is the lymph node. This is just an example that I'm showing you here. This is one lymph node. This is also one lymph node. This is one lymph node. This is also one lymph node. So this is the abdominal lymph node. This is the abdominal city. Sorry. This is cervical. Yeah, this is basically abdominal images where the lymph nodes are located here. So in our this study, what we have done, we have taken computer tomography images where we have used one public data set which is having computer tomography images of mediastinal lymph nodes and the abdominal lymph nodes. Okay, and in that data set, the data set that we have used, it is having the mediastinal lymph nodes of 90 patients, and total number of lymph nodes that were present in that image were 389. Similarly, the images, abdominal lymph node image data set also we have used, which is taken from the 86 patients and having the total lymph nodes of 595, right? So for this, now, as I told you that medical image segmentation is need to be performed, medical image classification is need to be performed. So for that, we need to select the deep learning architecture. So we have selected the very basic deep learning architecture, that is UNIT, which is very popular for image segmentations. Okay, so from the literature, from understanding, after understanding from the literature that the UNIT is good for the image segmentation, we have taken the UNIT for our intended task. Okay, and we had applied some another, we then did some modification that in that UNIT, so that our those lymph nodes can be detected correctly and they get classified, or the disease can be diagnosed accurately from that data. Okay, so what we had done exactly, that I am going to tell you here now. This is existing approaches are there for lymph node detection. So basically, whatever the lymph node detection is there, which has been done in earlier studies, that was having a problem, or being actually done by the manually by the radiologist. They are having the problems that I already described: intra-observer variability, structure, and all that things. You require feature selection and then calculation. You need to perform pre-processing staging, pre-processing steps. The shape and sizes of the lymph nodes vary with the patient to patient. So that sort of this sort of problems limit the use of manual segmentation and classification, or even the very basic algorithms or conventional machine algorithms cannot be used for this task. Okay, they are having these limitations, right? So when this manual or machine learning, conventional machine learning algorithms were used, they have detected the lymph nodes based on one criteria, that is enlargement of the lymph nodes. As I told you that when the cancer happens, then the enlargement of the lymph node happens. So they have just detected whether the lymph node size is getting greater than 10 mm or not. And on the basis of that, they are assessing whether it is cancerous or not. But they are neglecting the small lymph nodes having clinical importance. But it is not like that. Lymph nodes smaller than 10 mm size are not clinically important. They also need to be assessed, because see, when we are taking the when we are assessing the effect of the medication, if we are assessing the growth of the lymph node, okay, in one visit it is smaller in size, in another visit it is increasing in size. So we should see all the sizes of the lymph nodes. We cannot say that yes, I will see only the lymph nodes which are greater in 10 mm size. It means that you will be only looking at the final stage of the cancer. Okay, you're not doing the early stage detection or assessment or estimation of the possibility of the cancer is not being done. Okay, so that is why these all existing methods, manual and conventional machine algorithms, they are having these limitations. Okay, so this is already I discussed, so I will quickly go to my next slide. So here in this our work, we have used unit structure. Okay, this unit is basically having two parts. First one is the encoder and second is the decoder. Okay, and we also named as contracting path and expanding path. Okay, contracting path means there's in that contracting path, what happens, the data size, if I'm giving say an image of 256 by 256, it is going to be reduced in size gradually, and thereafter in the expanding path, it will be further increasing the size and it will become the same size which I have given at the input in my contracting path. So that is how it works. Even in unit, what happens when the unit learns, when the training of the new unit is being done, it is actually provided with the two data sets, two things. Okay, first one is the input data and the ground truth of that input data. Okay, so when the training happens to the unit, so आपने input image को unit में दिया, unit will compress that data and again it will expand that data. Obviously it will be doing a lot of things on that data. It doesn't mean that it is just doing contraction and expansion. Okay, it will be extracting the useful information and will be performing the intended task of the segmentation. Okay, so whatever the output will be there from the expanding path, that will be compared, or that need to be exactly same with the ground truth, and it will be keep doing that, keep learning that unit structure architecture will be keep learning. When I'm saying that unit architecture is learning, it means that it will be it is learning in such a way that it will reproduce the ground truth at the output of the expansion path. Once it is done with that, then you will say that yes, this unit is now trained. And once your unit is trained, then you just remove the expanding path or your decoder part, and in the encoder you give the test images, and at the end of the encoder you will be applying one classification layer which will be classifying the pixels, pixels in such a way that yes, this pixels belongs to my abnormal or my lymph node, or rest of the pixels are not lymph node. So it will be, that is how the segmentation will be performed. Okay, so unit is basically a fully convolutional neural network that it involves only the convolutional layers there. There is no fully connected layer. Connected layer and fully convolutional layer, there is a difference. So it is having only the convolution stages. Only the convolution layers are available here. Okay, so and it is this unit actually performs with very few training samples. Means if your data is less, in that also this unit structure is really able to perform well, because as I told you that it actually tries to regenerate the target image, okay, your ground truth. So due to that, what happens, it will go image by image. So say that if I'm giving one image, it will try to generate the exact ground truth for that one image, and it, unless until it attains that, it will be keep learning. Okay, so that's why it is learning is very good. So it learns with the smaller data sets. Okay, and when and that is why it is popular, because in medical, especially medical imaging, collecting large training data set is really difficult, because all of you know, those who are scientists here and they are doing on the medical images, we have to go to the hospitals, we have to request them, we have to get that medical images. Even for that, you have to do a lot of writing work. Okay, there need to be ethical permissions required. patient consents are required at the where you are taking the data sets, and using the data in our research work, that further requires the permissions from your research institute as well. So there are many, it's not that very easy to get larger data and for doing the task of medical image segmentation and classification. So that is why this unit is why it is popular, because it works very good on even smaller data sizes, right? But of course, not as small as what you are using conventional machine learning. Obviously, more than that is required, right? There are skip connections in the unit architecture which actually collects the multiple encoding feature extraction levels, okay, and connected these two different decoding levels, okay. Now, what exactly is this skip connection? I will tell you that this enhances the predicting capabilities of the unit architectures, and simultaneously this also limits the unit extracting similar low-level features repeatedly. So it is very much possible that when you are going from the encoding stage to decoding stage, in the decoding stage, similar information is being regenerated. So that can be avoided by doing the skip connection, okay. And it is not only avoiding the regeneration of the features, but it will also improve the predicting capabilities of the network. What is that skip network? What it involves? How that unit architecture looks like? I'm showing that with in my next diagram. So you can see here, this is the unit architecture. You can see this is my input image here, okay. This is going to be given to this is my convolutional block, and I'm writing here CP. CP means contracting path, right? When I'm saying CB, this is a convolutional block, and what exactly the elements of the convolutional block, they are briefed here. You can see there is a convolution, two-dimensional convolution will happen. There will be having the batch normalization. Then after that, batch normalization is nothing but actually we are normalizing the data in the batches. Okay, and why it is required? Because instead of processing the whole data in one go, if we are doing that processing the data in a batches, then that activation layer will be requiring will be having the less burden. Okay, so it will go to the activation layer. So here it is on the basis of these features, they are being classified or detected. Okay. After this activation layer. So output of this activation layer again is going to the next convolutional layer. Okay, again batch normalization is there, again activation layer, activation function is there. See, you can have multiple convolutions. That's what I was telling you, that when you people perform this multi-level convolutions, that is how you people are making the learning of your architecture deeper. Okay, so I'm learning with the low level feature, medium level features, high level features. That is how it will do. That is how it will work, right? So you can see after the convolutional block, the size here becomes 256, 256, and 32. But after that, I'm applying the max pooling here. This is M block, M1. That is a max pooling. So I already told you about the max pooling. It will take the maximum value for the regions. So I have applied the max pooling here, and I have reduced the size of my data from 128, 128, 32 to 128, 128, 256, 256, 32 to 128, 128, 32. Isn't it? So I have reduced the data. And thereafter, again, I am giving it to the next, my convolutional block, again going to the next max pooling, again going to the next convolutional block, again doing the max pooling. And here, likewise, I will keep going like this. And here you can see this max pooling is now having the size of 16, 16, 256. So 16, 16, this is nothing but the size of the image data. Okay, so it has reduced now from 256 to 256 into 16 into 16. Okay, and this 256 is nothing but the filter sizes that I'm using in my convolution. Okay, and here at the end of this encoding path, now my data has been encoded, and you are having one center stage here, and this center stage is having, the center stage or center block is having this structure. It is having convolution again, batch normalization, activation. Then there is a dropout also we are doing. We are removing the inactive neurons from our network, and again we are doing convolution, batch normalization, activation. Now many of you participants must be having a question, sir, how you decide that how many convolution layers, how many activation function layers that you are going to build in your unit. So let me tell you, let me clear you this. Let's see, in deep learning or machine learning techniques, it is really important that you try, for your data set, for your application, you try with all the, you try to build an architecture by all the possible combinations. Means you know about that. Yes, if I'm increasing the convolutional layers, if my learning is getting better, increase it. Okay, if I'm using this activation function and if my performance is getting improved, use it. If I'm doing this pooling and I'm bettering my performance, use it. So you have to choose on that. Okay, you have to choose on that, right? So here, after this encoding path, there is a decoding path now. You can see this SC4. SC4, that is a skip connection. This is what I was talking about in the unit. That is very important. That I am taking directly the data or features from this convolutional block to this skip network. Okay, this is my skip connections. Here also, every convolutional block, after the convolutional block in every convolutional block in the encoding path, whatever the features extracted by that convolutional block, I'll be directly using it here for doing the convolution of my this encoded data. That is what is the advantage. And why I'm doing this, what is the advantage? If I do this, I'll be increasing my prediction capabilities of the pixels those belongs to the lymph nodes. That prediction will improvise. I'll be able to directly get the low level features. I will need not to repeat the calculation of the low level features again. Okay, that is how I will reduce my excess network parameters. So my network parameters will be reduced, my computational complexity will reduce, and my network will not suffer from the problem of overfitting. Now, what is overfitting? Overfitting is something, say that if I have a huge data set, if I have huge data points into data points, and if I want to divide them into the two categories, I'll be linear. If I use a linear line, then it is made possible that some of the data points get wrongly classified, isn't it? So for that, what do? You do a linear, non-linear, what I will say, non-linear curve will be there, which will be segregating the data points into the two categories. Okay, so that exactly all those nodes can fall on that category. Okay, so when we do that non-linear fitting, okay, so that non-linear curves are we generally perform, okay, by using the deep learning, that we want to do the classification accurately. But while to do that accurately, we actually overfit the data. Okay, so that is what is the overfitting. So we will save that problem. We will save our network from the problem of overfitting as well if we are using the skip connections in the unit. Okay, so that is what exactly has been done here. This is the skip connection 1, skip connection 2, 3, 4, and you can see it is now expanding. The size here 32,768. It will increase further, and it will become exactly same here after this convolutional layer, that is 256,256,1, which is exactly equal to your input. Okay, So it means that now here I'll be having two things. This will be my target and this will be my input image. So whatever the output here, it will be exactly, this network will keep learning, keep training itself unless until it regenerate the target or ground truth. Okay, that is why this is having a learning for one single image. The learning, it is a multiple learning cycles are there for learning from only one image itself in the unit, and that is the beauty. Okay, so let me just come back again, some describing you some theoretical here. Lymph nodes are having the class imbalance problem. Okay, as I told you that there are similar structures around those lymph nodes in the same image, so that's why there is a class imbalance problem is there. And it is really important in that case, say that you people are having a picture where there are many different type of the balls are there. Okay, now in that picture you exactly want to see or you want to locate a cricket ball. So it means that you have to focus on you have to look in that image and you have to exactly find out your cricket ball in that image of different balls that are available in the that are used by the humans, okay, for playing many sports, different sports, right? So in such task, basically you have to focus on the target. So for doing that, we have taken one new trend of the deep learning that is called as attention mechanism. Okay, this attention mechanism help us to actually focus on the target structure. That is what exactly it is. And when I focus on the target structures, I'll be getting very good features. See, that is what is important. अगर आपको segment करना है तो your whatever your structure is there, that structure first should be localized properly, and after that, on the basis of the new pixels, you will be classifying, yes, this is belongs to the lymph node and this does not belongs to the lymph node. Okay, so for doing the task we have used the attention mechanism here. Okay, and what is this attention mechanism? Basically, attention mechanism actually involves two types of work, that it will be doing the linear transformation followed by the non-linear transformation. And due to that, see, linear transformation, it means I'll be using some linear activation functions and converting my data, and again then after that I'll be using non-linear transformation. So while doing that, what happens that it will be able to identify the pixel, those are increasing the non-linearity. It means those who are belonging to the one particular what I say biological tissues. So that is why this attention mechanism is very successful in targeting, in focusing on the target structures, right? So this is actually followed by using this simple mathematical formula can describe you here. You can see this is alpha is equal to sigma f at a double t, that is x comma g, that belongs to theta att. So what exactly is this? Alpha represents the attention coefficients are there. These are the coefficients that we generate by using this function. Okay, this sigma is nothing but the sigmoid transformation function, that is non-linear transformation function, right? And in that non-linear transformation, what data I'm giving theta at attention. It is characterized by the features of x and g. Okay, so this x and g, what this x and g is there, this x is nothing but my input and the target one. Okay, so these values will be this theta attention will be getting these values after the linear transformation. So by using x and g, on the X and G, you will be first performing the linear transformation, and that data will be further given to the non-linear transformation by using the sigmoid function. That's what exactly is there happening, right? So this is simple unit. This is a residual unit that we have used. Another unit modification that we have done here, we have used the concept of residual. What is residual? Basically, if you people are able to understand residual, when you call residual, when you use the residual term, because where you require some memory, where you require some past data, okay, which is or when you required the data from the earlier stages of your process, that is what we call as a residual. So here also we have used that residual block as well to improvise our attention unit mechanism. So yes, attention mechanism, we have applied attention, we have taken plain unit also, we have applied attention also, we have applied resonate also, residual concept also, just to check that which type of unit or which modification that I'm doing in the unit will perform good segmentation of my lymph nodes. So for that we have done this experimentations here. You can see here the residual unit is there. So what is this residual unit? In the convolutional block, it is very similar to unit. Only the thing is that in the residual block, in the convolutional block, we are taking in this, after this batch normalization, we are again taking the data from the previous stage and using data from this batch normalization, and the data from the earlier stage are actually merged, and thereafter it is going to be given to the activation function, and that is going to give you. Why this will help you? What happens in many times, say that I'm having, just let me give an example that there is a baby, okay, that baby is learning from learning about the balls from the images, right? So it will learn from the different images. I'm showing it a football image, then basketball image, then cricket ball image, and I'm saying that this is a ball, this is a ball, this is a ball, this is a ball, right? Okay, now I have told them that yes, this is a ball. Now the ball, that baby learn from that, yes, anything that is circular in a shape, that is called as a ball. Okay, now after that I want to teach a baby that this is not simple a ball, this is a cricket ball. Then I have to again give back that image of the cricket ball to the baby and have to tell that yes, this is a cricket ball. And at that stage the baby will understand something which is circular in shape is called as a ball, but and if it is having some stitches or if it is red in color, then it is a ball, but it is also a cricket ball. So that is how it learns. It's just like that we are doing here in the residual concept, basically. Okay, so that is a simple example that I wanted to share. This is here, we have implemented the attention mechanism in the unit. So you can see what is that attention block. We have added one attention block in the expanding path here. You can see this AB3, AB2, AB4, and sorry, this should be AB1 basically. This is AB4, AB4, AB3, AB2, AB1. Okay, now what is this attention block? In that attention block, we are doing that transformation, linear transformation. So you can see I have applied here activation function ReLU, that is a linear transformation. I have applied here activation function sigmoid, that is doing the non-linear transformation of the data. Okay, and that is how my unit structure will be able to focus on the target structures, target lymph nodes. It will not waste on time focusing on another structures in the images. Okay. Secondly, we also have used a new trend in the machine learning or deep learning that is most widely used nowadays. That is a transfer learning. What is transfer learning? Transfer learning it means that say that you have designed one architecture, okay, and that architecture is actually you have designed to classify say cricket say balls, okay, and you have another architecture which is already trained for the coins. You know that coin shapes are also very similar to the ball shapes. It is also circular and that is also circular. Then you can save your time in training your architecture for the balls to make your network learn that yes, the ball is circular in shape. Okay, instead of giving that learning to that architecture, why not to borrow the learning from the coin architecture directly to detect a circular shape, to understand the circular shape. So you can directly transfer that learning. You need not to make your ball network to learn that. It's not required. You can do the further learning of that network from over to that. Or if I'm giving the learning circular shape, as I told you that circular shape, every ball is having the circular shape. So that is already learned. Okay. And we can borrow that learning from some another network, and we can do them thereafter. We can do further learning of cricket ball, basketball, and various bouncing. If something is bouncing like this one, then this is that ball. So you can do the further learning to that network instead of doing the basic learning of the circular shape. Okay. I'm having some questions in the chat, I think. Am I still audible, Doctor, ma'am? Yeah. Yes, it means what this message is not about. Okay, fine. So this is what about the transfer learning. So what we have done, mediastinal lymph nodes and the abdominal lymph nodes, they are having a similar structures. Okay, and that is why we had attempted to transfer the learning from the mediastinal neural network to the abdominal network, and we also tried the vice versa. Just to understand, say that if some doctor is there, okay, some radiologist is there and using this my cardiac system, right? He wants to detect the abdominal lymph node, right? But for giving the necessary training to that network, he's not having the data set. Okay, but he is having a trained network for the mediastinal lymph nodes. So he can directly borrow that learning from the mediastinal lymph node to the abdominal lymph node network, and he can do the testing of the abdominal network. That is very easy. So in case of lack of data for the training, the transfer learning is really useful, really fruitful, really important, right? So that is what exactly we have done here, and we could able to do this because anatomical structure similarity is there between the abdominal lymph node and the mediastinal lymph node. And if we perform this kind of transfer learning, our system is becoming more fast and robust. Okay, because your training time is actually saved, so your system is going to become fast. Okay, so we have tried here to fully do the full transfer learning, partial transfer learning, and no transfer learning. Okay, that experiments we have conducted here. So you can see our total lymph node segmentation or lymph node detection experiment architecture is like this one. Here you can see this is the input CT image. Then we are doing the CT windowing. CT windowing in the sense that we are actually trying to increase the contrast of the image so that the different biological tissues or the different structures can be easily visible to us. Okay, or more information can be extracted from that data. Okay, This we had done by using the Hounsfield units, by adjusting the Hounsfield units that we had done. And thereafter, we have applied the data augmentation. Now, this is another new trend that is being used in the deep learning. What is data augmentation? Basically, when you people, as I told you in the beginning itself, that deep learning architectures require large data set. But it is not always possible to have a larger data set. You may have a smaller data set. So from that smaller data set, you people can create the larger data set by doing the data augmentation. Means you can increase the data size by doing some mathematical operations, and by after that you'll be having the larger data set, and that can be used for training your deep learning architecture. Okay, so that is what exactly we have done here by doing this data augmentation. Then we have a different attention unit architecture here for abdominal lymph node. So this is totally abdominal lymph node, and this is the second part that is for the mediastinal lymph node. And we have done the transfer learning also. So we are transferring the learning from the mediastinal to abdominal and the vice versa. So that is what exactly our experiment protocol that we had designed for our this study. Now, what is this city windowing and data augmentation? City windowing that I already told you, it is based on the Hounsfield units that we have done the city windowing. Okay, and we have applied the data augmentation. Now, data augmentation are basically some kind of geometrical and statistical transformation methods are there, which are used to increase the data size. Okay, without actually collecting the data. So you're not collecting the additional data. Instead of that, whatever the data, small data you have, by applying some geometrical and statistical transformation, you are increasing the data size. That is what exactly we have done. It is actually, we have used elastic deformation as one of the statistical tools to do that all the transformation and to augment the data. Okay, elastic information actually incorporate the variation in the data set by corresponding to corresponding to the lymph node city appearance taken while patient movement or the pose variation. So say that when you people are taking the city image of one particular patient, then that patient can have some angular movement, or it can the data can be flipped. Okay, means you have asked the patient to lie down like this one, but now this time the patient is lying down this way. So that is what exactly we have done. And by doing that all flipping we have done, then we have given the data to the angular rotation, and that is how we have actually increases the images. Our data set, that is how we increased. So as you from our my initial data size database description, as I told you, we were having 595 abdominal lymph node images that we have, by using the data augmentation, we converted into the 5,595. Likewise, mediastinal we have converted 388 into 5,388. So you just imagine that how much number of data augmentation that we have performed, right? I will tell you that how it has improved our performance, that I will show you. Okay, now let's go back to the training configuration of my different unit structure, attention unit, residual unit that I had implemented in my study. So in that we have used rectifier linear unit. We have used convolutional kernel sizes of 2 cross 2. It is a 2 by 2 matrix, or it is 1 by 1 matrix. Then there is a for this whatever the values in this convolutional kernels are there, those values are initialized by using the Glorot uniform function. Okay, and we have used the loss function. Loss function in the sense, you know that in the attention unit structure you have to attain the ground truth. So whatever the output will be generated from the decoding path, it will be compared with the ground truth. So we have done that comparison, and there is a loss function that we are using to assess that comparison. That loss function is binary cross entropy and dice loss that we have observed between the ground truth and the output of my unit. And if that loss function is not not below my threshold, so I will be keep learning my unit for that single image itself. Okay. And summation of these two actually loss functions, binary cross entropy and dice loss, is used with class weights. We also use the class weights. So class weights in the sense, I am telling you that yes, as I told you that I have two classes here, benign and malignant. So I'll be giving the class weights initially. Okay, and after doing one by one, after assessing the loss functions, my class weights are being actually getting updated. Okay, and I'm checking the value of the class, those class weights are below my threshold or not, and accordingly then I'm doing my training. We also have used five-fold cross validation. What is five-fold cross validation? Basically, see, in order to better your learning of the machine learning algorithms, you give a data in a different, you do not give a single training. Say that I have 100 samples, so I'm giving first 90 samples for the training and rest of the 10 samples for the testing. So that is a simple training is there. But if you are doing the training of your network in such way, there will be a problem of generalization, there will be a problem of the reliability. Your network will not be reliable, your network will not be a generalized network. Okay. Instead of that, you give a learning in you do the cross validation, five-fold or 10-fold cross validation, and after that will give the proper learning to your network. Okay, what is that five-fold cross validation? Say that I'm having 100 samples. So in first fold, I'll be giving first 90 samples as a training and second and remaining 10 samples as a testing samples. In the second fold, I'll be giving training samples from 20th to 100 samples, 20th to 100 samples as a training samples, and first samples from 1 to 10 I'll be using for the testing. In my third fold, I'll be giving some say 30 from the 30 samples to up to 10 samples. Means, and 21 sample to 30th sample I'll be giving to for the testing. So this is how these folds need to be applied. So they will be increasing the generalization and the reliability of your proposed machine learning or deep learning architecture. So these are the loss function that I was talking about by binary cross entropy, dice score, and there is a dice loss also. It is just a 1 minus ds. So dice score is going to be subtracted from 1. So that is what exactly is there, right? So we also have measured the evaluation of our proposed algorithm we have conducted, and whether it is lymph node or not. On the basis of that, we have measured these 3 evaluation parameters. The first one is the sensitivity, second is the dice score, and third one is the Hansdorff distance is there. That is what we have calculated. Hansdorff distance is nothing but how close your output is to the target output. Okay, that we had calculated, and that average value is actually telling us that yes, your outputs is very close to your target structures or your ground truth. So that is what exactly has been done by using this mathematical formula. So this is all even being done by pixel by pixel. Okay. And these are the results. That is what I was telling you, that we had implemented segmentation mate. There is a already available one image segmentation network is there, deep learning network is there, that is called as SegNet. And then we had implemented unit, REST unit. This is all we have. I have told you, I have briefed you about all these networks. Attention unit. So this we have applied for abdominal lymph nodes. We had applied it for the mediastinal lymph nodes, and we had calculated the sensitivity, dice score, and the Hansdorff unit. And Hansdorff distance. And here I found that attention unit is performing far better than all these 3 networks that we had re-implemented for our own data set. Okay, so that is what exactly has been observed here for abdominal lymph node also, and for the deep mediastinal lymph node also. both the lymph nodes over this attention mechanism involved modified unit is performing better. Even you can see 99% sensitivity is there. Dye score is 97% is here in the mediastinal lymph nodes, right? As I told you that we also have done the transfer learning. So yes, here you people can see this F stands here, the full transfer learning. Full means complete weights and complete training parameters from one deep learning architectures are adapted exactly as it is to the next another network. Okay, and we also have done here the partial. So I'll not be taking the weights of network parameters or weights of my all the layers. I will be taking it for some convolutional layers, and then that is only being transferred to my this another structure, another architecture. So that is called as a partial transfer learning. So we have done that in this for the detection of the abdominal lymph nodes. We have done the full transfer learning, that we have fully transferred the learning from the mediastinal deep learning architecture trained with the mediastinal lymph nodes. We have taken the full transfer learning, but with that the performance was coming very poor. Okay, but when we have taken the partial transfer learning, then the performance is coming 84%, 87%. Okay, and if we are not doing any transfer learning from the mediastinal lymph nodes, we are training our abdominal lymph node network with its own data set of abdominal lymph nodes and doing the testing with the abdominal lymph node itself, then in that we are getting the best performance. Okay, but the thing is that we need to understand here, even with the partial transfer learning from the mediastinal lymph node, we are getting a very considerable performance here of 84%, 87%. That is a good sign. It gives an indication that yes, the transfer learning works. Okay, the transfer learning works. In a scenario where you are not having the data for training your architecture, you can borrow the training from another architecture and you can test your data set. So in that scenario, it is not like that. It will give you totally wrong results, but it will be giving you some 80-84% accuracy or 80-84% sensitivity, and dye score is there. Okay, so that is a good sign, and that is a motivation to adopt transfer learning as one alternative. Or okay, we also have done the transfer learning from this abdominal lymph node architecture to the mediastinal lymph node, full adaptation, partial adaptation, and zero adaptation. So obviously, if I am not adapting anything from the network, another network, I am training my network with its own mediastinal lymph node database and testing it for the mediastinal lymph nodes itself, then the performance is the highest. But if I'm transferring partial learning from the abdominal lymph node architecture to the mediastinal lymph node, I'm getting a considerable performance as well here, 89%, 90%, and the hands drop distance of 2.02. So that is a very good performance that I am able to attain by using the partial transfer learning. So this indicates again that yes, the transfer learning works. So these are some sample results of the segmentation that you people can see. We had done this automated segmentation by using attention mechanism, attention unit, and you can see this automated detected lymph nodes are exactly here. Okay, so in such images, we are able to automatically detect the lymph nodes by using the automated computer algorithm, deep learning computer methods. Okay, these are some results of the abdominal lymph nodes. These are some of the results from the mediastinal lymph nodes. We also have compared our implemented algorithms here with the number of training parameters, because this is very important as well, that you should see that how computational complex your algorithm is. So that also we had done. So by comparing the parameters, so there are basically two types of parameters, training parameters, and there is a non-training parameters also. So in SegNet, we are requiring this much amount of parameters, total 1,36,09,089, while in this 3 crores, 3 crores. So we know that unit, ResNet are giving the lesser performance. It is not, there is no question of adopting SegNet because its performance is far poor than all these 3. This is poor than all these 3. So that's why the comparison is need to be focused more on these 3 networks. Okay. So if you compare here in my attention unit, the training parameters are increased a little bit. There is a 7% additional parameters are increased in the attention unit, but with that 7% increase in the parameters is giving me an accuracy increase of accuracy of around, you can see I'm able to have 2% accuracy boost here. Compared to this unit, I'm having the 4% accuracy improvement here. If I will see here, it is 10%. If I see here, it is 3%. So in order to have the better performances, for having this such a higher performance, we can bear that cost of computational little increase in the computational cost of 7%, isn't it? So that is what exactly is there we observed. Okay. At the same time, we also have seen the computational complexity, that is if I'm doing the transfer learning. So that is true only for the attention unit. And we come to know that in the partial adaptation, full adaptation is totally poorly performing. So I'm not considering this. I'm considering only the partial and zero adaptation. So in both the partial and zero adaptation, you can see that total training parameters are almost equal. Okay. So with the equal parameters, if you are getting the considerable performance, and that too by partially transferring the learning from one network to another network. So it is really a good, what I'll say, successful task, I will say, successful transfer learning, because that will be saving you a lot of time in training your network with the complete data set. Okay. So this is the conclusion of our work. Yes, we had implemented unit-based architectures for the detection of the lymph nodes, both mediastinal and abdominal. And for that, we have used the data augmentation, we have used the transfer learning, and we come to know that our attention unit is having far better performance. And it is the best. Even we had compared its result with the studies done in from the literature as well, and we come to know that our attention unit is the best deep learning architecture proposed till date for the lymph node detection, right? So with this, I'm done with the part of my segmentation. There is a further part of the classification as well, but I think as the time is limited now. The class is ending at 12 p.m. So I will stop here, and instead of going further, because that will be needing another 30 to 45 minutes to complete the task of medical image classification. So that I will do in the next session, that is starting from 2 p.m. Okay. And in that, we also give you some demonstration or giving you the hands-on session where we will show you how to implement the unit architecture in using the Python. Okay, using Python. Okay, on the Keras platform. Okay, that we will show you, and we will also show you how to perform the task of image segmentation using the unit. Okay, and further doing the classification task by using our fully connected network. Okay, so I will first complete this diagnosis part or classification part in the next session, and thereafter we will give the hands-on session regarding the designing of the unit and one deep learning architecture for image segmentation and one deep learning architecture for the classification. Okay, so that is what is the plan for today. I hope you have understood what I taught you, If you have any queries, please put it in the chat box, and then accordingly I will answer those queries. Am I audible to all?
Yes, sir. We can hear you, sir.
Okay.
You are
Ma'am,
audible, sir.
if there are any queries from the participants, those queries can be addressed quickly, and because as the time is limited, so we will end up the session, and in the next session I will continue.
Sir, I request all the participants to post the queries in the chat box. I repeat, I request all the participants to post queries in the chat box. Sir, till now
See,
there are no queries.
I have to tell this to the participants with a humble request. See, I truly understand those participants are there, they are faculty members, they are already involved in huge online teaching and learning nowadays, because there are many FDPs and there are many courses are going on online, and you are getting, but you take it as a positive thing. See, the knowledge, this is the first time, because of for whatever this reason of pandemic, the knowledge is being shared in such a large in such a large level. Okay, it's a huge knowledge is being shared now by using this online mode, and I truly request all the participants that receive this knowledge. You won't get such an opportunity again. This is the right time, this is the right platform that has been designed by the government also, because Swayam courses and those Atal courses, why they are floating this, that yes, this knowledge, huge knowledge can reach to you. Okay, and you, so that you people get motivated, you people can start your own research, and you can learn new things. And whatever I taught in my today's class, that is something very new. This is our recent work. You people can understand. You people are able to understand deep learning, attention mechanism, residual mechanism. You are able to learn transfer learning. Okay, how to apply that into on the medical image segmentation, that you are able to understand. You will be further able to understand in my next session about the classification as well. So this is an opportunity. Don't take it as a too much programs are going on, how many programs that we should attend, how much we should learn. Don't stop yourself from learning. This is you have a time, and even this is a part of your job as well, because this is not being considered as this is your private activity. Your institute has only asked you to participate in this FDP so that your knowledge increases, you get enriched with the advanced technology. So this is an opportunity, and accept it with the open hand. Yes, you can unmute and ask any query if you have in your mind. If it is not there, it's okay, fine. Maybe in the next session, you people can put up the queries. Okay, so ma'am, I think there are no questions from the participant side. So I think I will stop here, and we'll meet in the next session from 2 p.m. now. Is it that?
Okay,
is it
sir.
okay?
Yes, sir. Okay, sir.
Okay, ma'am. Okay.
So
Okay, participants, thank you so much for attending this session. I will meet you in the next session from 2 p.m. And as I told you about what I'm going to teach into the next session, that will be followed. I hope that you will be present in the similar number in that session as well, and you will learn better than this session as well, better than this session also. Okay, so that is what I expect, and thank you so much. See you in the next session at 2 p.m. Thank you.
Thank you, sir.
Okay, ma'am, can I leave now?
Yes, sir.
Okay.
Thank you so much, sir. You have explained so clearly, sir. Today's session, morning session, is so clear, sir.
Okay, thank you so much, ma'am. Thank you so much. Looking forward to meet you at 2 p.m. Thank you so much. See you, participants.
I request the participant to join the class at 2 p.m.